All right, section 1.1, functions and function notation. So we're jumping right into something that we would have done in Algebra 2. So our definition of a function, function f is the name of the function. This particular function that we're talking about here. A function is a rule for a relationship between an input quantity and an output quantity in which each input value uniquely determines one output value. We say that the output is a function of the input. Now, here's what that means. I know that's a lot of, we get these definitions in math and it's a lot of words, but here's what that means. It means, like, if you would make a t-chart for a function and you put in your input value, which we usually call the x's, and then you have an output value, which we usually call the y's, or in function notation we use a little different way of writing it, but we're just going to leave it for this right now. When we put in, for instance, a 2, you remember how we did that when we put in a 2? We do the math and then we get an answer, right? And we don't have to guess, we don't get like multiple answers, we only get one answer. And as long as it's a function, for every input value, it uniquely, that means there's only one that goes with it, it uniquely determines the output value. So in other words, if you put in a 2, you're only going to get one answer out. If you put in a 5, you're only going to get one answer out. So this 2 determines whatever's going to come out of that function, and whatever input value you have does that. So the input value determines only one output value. That's what happens with a function. The input quantities are called the independent variables. And again, I mentioned usually we call that x, but it really could be anything. If we're dealing with a word problem, we might use different letters instead of x and y. The output quantities are called the dependent variables. And the reason for that is the input quantities you get to choose. So they're independent. You just pick whatever you want. Like an independent person, they just kind of do whatever they want, right? So the independent variables are the ones you get to pick. You get to pick whatever you want. The output quantities are the ones that are dependent on the input. So here's an example. At a coffee shop, the menu consists of items and their prices. Do you think the price would be a function of the item? Or do you think and I guess the other part of that is, do you think the item would be a function of the price? So in other words, if you pick something at the shop, does that item determine the price you pay? Or do you kind of go in and pick a price and then that determines the item you're going to get? No, you pick the item and that determines the price, right? And usually they set that price based on like how valuable they think the item is, or how much work it takes to make it, or whatever. So is the price a function of the item? Yes. The item determines the price. Right? So if you go to Walmart and you pick up an item and you go up to the scanner machine, you scan it and it tells you the price, right? If you scan it again, it should hopefully tell you the same price. If it tells you a different price, there's a problem. So the price is determined by the item. So the item would be the independent variable. The price would be the dependent variable, because the price depends on which item you're looking at. Is the item a function of the price? So in other words, if you went into Walmart or any other store, I guess a coffee shop in this case, and you chose a price and you looked at the menu, would that one price determine only one other item? Or determine only one item? Or could there be multiple items that had the same price? There could be multiple items. And in fact, if you go to a coffee shop, if you get a large of one sort of beverage, it's going to be a price and probably the same price as a large of a different type of beverage, right? I don't go to coffee shops, so I couldn't even, I know there's cappuccinos and all these other random things, but they could have the same price. So remember that the item going to its specific price, that's going to be a function. Because if I look at the item on the menu, I can figure out the price. There's only one price for it. There's not two prices for it. But if you know a price, does it make sense there could be multiple items that all have that same price? Oops, item. Oh man, I'm having trouble writing here today. We'll say item 1 item 2, item 3. There could be many items that had that same price, right? And so that's what makes the item not a function of the price, because the input value does not determine only one output value. And for a function, it has to be only one output value. Definition, again, so we're going to talk about the words and then we'll try and explain it. Sometimes in a relationship, each input corresponds exactly with one output. Okay, so we already know that in a function, the input determines exactly one output, but this is saying that every output corresponds to exactly one input. So this would be like, Walmart's my go-to example for functions. So I talked about if you take an item to the scanner, you scan it and you get one price, right? You scan it again, you get the same price. That's an example of a function. But in this case, this would be like, okay, so that's a function, but at Walmart, there are probably multiple items that have the same prices, right? So in this example, it'd be like you go to Walmart and every item had its own unique price. So if you went to Walmart and this was the case where every item had its own unique price and you knew the price of an item, you could actually figure out what item it was, because every item has its own unique price in this situation. That's what we call a one-to-one function. Every input goes with exactly only one output, and that output only goes with that one input. And that will happen sometimes in math. It does not happen all the time in math. And we're going to figure out when does it happen and when does it not happen. But that's an example of a one-to-one function. All right, so here's our function notation. This can be a little bit tricky sometimes, so I may simplify it so that there's less words and more letters. But here's the notation. The output is equal to f of the input. It's not times, but the function, when it is applied to the input, gives us the output. It defines a function named f, and this would be read as the output is equal to f of the input. Now, how do we usually see that? We would see like f of 3 equals 10 or something like that. I guess I wrote that backwards. But anyway, here's the input. Here's the output. The function is applied to the input of 3 in this case, and the output in this case, just an example I made up, is 10. Now, what does that mean? Well, that means if you were making a t-chart, the input value was a 3, and the output value was a 10. Because your inputs are typically your x's and your outputs are typically your y's when you're thinking about graphing them. So this f, just remember that f does not mean multiply. It's not f times 3. It means that there's a function, a set of directions, or a relationship of some sort that is applied to the 3. And then based on that, you're going to get your output. Introduce function notation to represent a function that takes as its input the name of a month and gives as the output the number of days in the month. So here's the idea. This function, I tell you a month and you tell me the number of days in the month, right? That's what the function is supposed to do. So let's just call this function capital F. Now, there's no equation for this, right? There's no equation, at least I don't know of any. There's no equation we can make up that will just tell us the answer. So the best way to do this one would be like a chart, to represent as a chart. So let's call our input M. I'm being very creative. M is going to stand for month. And our output is going to be D. Again, I'm being very, very creative. What do you think that's going to stand for? Days. Days in the month, right? So what we have to do is make a table to help us represent this. So our first month is January. When the input is January, what is the output going to be? Do we know how many days are in January? It is 30 or 31. It's 31. January has 31 days. Okay. When the input is February, and we'll assume that this is not a leap year, what would the output be for the number of days? 28. February is that's the weird one. And what do we got? February, March. If March is the input, what is our output going to be? How many days in March? 31. April. And we can use our little knuckle method or whatever, but that has 30 days. May has 31 days. June has 30 days. And so we could keep going, we could finish the whole table, right? And we are using a table to represent a function. Now we know it's a function because of this. If I ask you, how many days does June have in it? There's only one answer, right? How many days does June have this year? That's how we'll say it. How many days does June have this year? Well, there's only one answer. June has 30 days this year, right? And that's what happens in a function. There can only be one answer. If I ask you how many days does September have this year? There's only one answer. If I ask you how many days does December have this year? There's only one answer. And that is what happens with a function. So we could fill out an entire table representing this function. And if we wanted to use our function notation, here's what it would say. I called my function capital F. What letter did we use to represent our month? M. So with the input of M, and then the answer or the output was D. So if you're wanting to use function notation, here's what we could say. This is how we defined our function with this table, and we would finish the table. But then when we actually write out the notation, F, this function applied to the month, will give us the number of days. Now it's not an algebraic function, it's a table function, but that's how that works. This is actually our final answer, but I wanted to make sure we understood what F meant when we were talking about that function. Example 5, a function n equals f of y. So f is the function, and they've defined it as input is what here in this case? According to this statement right here, what is the input for our function? What variable represents it? Yeah, it's y. And then what is the variable that represents the output? The n. Okay, and then we know f is the name of the function. So a function, n equals f of y, gives the number of police officers, n, so that's what n stands for, in a town in year y. So y is, that's what the y stands for. What does f of 2005 equals 300 tell us? What does that mean? This is in the place of the y, correct? And what did y represent? It represented the year. So you're exactly right. In the year 2005, there were, and then notice that the n, let's use a different color. N is, the 300 is in the place of the n. And so what did n stand for? The number of police officers. So in 2005, there were 300 police officers. So we've got our table here. They finished the table. Notice this one is set up a little bit differently. They didn't use January, February, March. They used the number of the month, right? First month, second month, third month. And so they filled out the table. And since the second one is a 28, we know this is like this year where it's not a leap year. But let's look at this. Table 1. This table represents the input number of the month. And then they give those examples. While the output is the number of days in that month, like we had done before, this represents everything we know about the months and the days for a given year, as long as it is not a leap year. Okay, so does that make sense that this is really the same table we were building before? So month number 1 is January, month number 2 is February, March, April, May, and so on. And then they have the days listed. So that is a table that represents a function. So if I asked us, we don't have a function name listed here. Let's just call it, what do we want to call this function? We can call it whatever we want. We get to name it. All right, let's call it, okay, we'll call it capital C for calendar. Okay, so what that means is, if I ask you for C of 7, what would the answer be? 31. Yeah, input value is 7, right? That's what this means. Output value is 7, output value is 31, right? If I asked you what is C of 12, what would that be? 31, right? Input value is 12, output value is 31. Now, if I was really mean and I asked you what is C of 30, what would you say? This is a kind of a trick question, but because what am I telling you here? I'm telling you the input value is 30, right? Do we have a 30th month in the year? Does our function tell us anything about the 30th month in the year? No, because there isn't one. So this is nonsense. So I wouldn't ask you that. So that's just to make sure that you understand, though, the input has to come from that input section. And I put a 30 in there because I knew there's a 30 down here on the bottom, but we can't do that. You have to have the input, the function applied to the input to give you the output. All right, here's another example. The table below here defines a function. Okay, now this time they tell us the function name is, now I want to be careful because sometimes they switch the order on us here. What is the name of this function? Or actually, maybe let's step back. What's the input value for the function? N, right? N is the input. Let's use blue. So N is the input. What is the output value of the function? Q. So maybe that will help us out. What do we know has to be then the name of the function? G, because that's what's left, right? It's always in the same spot. So the name of the function is right here, G. Okay? Remember this notation gives us G is the name of the function. Oh, you should have read further, then I would have told you the answer. And is the name of the function that takes the input value N and gives us an output of Q. So in other words, again, if I asked you what is G of 4, what would this table tell us? 6. G of 4 is 6. If I asked you what is G of 3, what does this table tell us? 7, right? So it's pretty easy to read a table. We just have to look at the input value and find the corresponding output value. Table number 3. This table represents the age of children in years and their corresponding heights. This represents just some of the data available for heights and ages of children, because obviously you'd have to write down all the children in the whole world, right, if you were going to have an exhaustive list. So the question that I have here is, notice the other two, it said this was a function, or it said the tables were a function. Is this table going to represent a function for us? Okay, you said no. Why not? Because not all children who are 5 are the same height, right? So notice here's the issue that we have right here. Remember a function? If you put in an input of 5 and the output is 40, the input or the output should always be 40 when you put in a 5. But notice one time you get a 40, but the other time you get a 42. That'd be like going to Walmart and scanning an item, and one time it says $5 and the next time it says $10. You'd be like, well, what's the actual price? So that can't happen in a function. So if your inputs are the same, if it's a function, the outputs also have to be the same. So this one is actually not a function. You have to be careful. Not all tables will give you a function. Now, the last two, they just told us, this is a function, this is a function. This one, they didn't tell us. And when we look at this, we actually find out this is not a function because of these two inputs being the same, but the outputs being different. Now that we know that, let's take a look at example 6. Which of these tables defines a function, if any of them do? So we've got 3 separate tables. If we look at table, we'll call it table number 1. Does this first table over here, table number 1, does this first table define a function with those 3 inputs and those 3 outputs? Yes, right? 2 gets mapped to 1, 5 gets mapped to 3, 8 gets mapped to 6. No problem. So yes, this is a function. Let's go to the second one. These next 3. Table number 2. Do those 3 represent a function? Yes, -3 gets mapped to 5, 0 gets mapped to 1, 4 gets mapped to 5. Yes, that is a function. Let's go to table number 3. Do those three represent a function or define a function? No. What's the problem? There's two 5s, and one of the 5s gets mapped to 2, and the other 5 gets mapped to 4. That's not a function. So we just have to be careful when we're looking at these that we can know how to identify if something is a function or not a function. Oh, I forgot to answer the second question about one-to-one. All right, let's go back. I need to read the whole directions. So the second part of the question was, are any of these functions one-to-one? Okay, well, obviously I've given away the answer on the first one, but how do we know it's one-to-one? Well, one-to-one means that every input goes to a different output. So 2 goes to 1, 5 goes to 3, 8 goes to 6. If all of these 1, 3, and 6 are different, then we know that that's going to be one-to-one because every input is going to a different output. How about this next one? -3 goes to 5, 0 goes to 1, 4 goes to 5. Is that one-to-one? No. What makes it not one-to-one? Yeah, because both the -3 and the 4 go to 5. Now that's okay. It's still a function, but it's not a one-to-one function. This example here is like you go to Walmart and you have two different items that have the same price. That's okay, but it's not a one-to-one function. That'd be like the very special store that every item has its own separate price. Okay, so this one is going to be not one-to-one, even though it is a function. And then this one, since it's not a function, we don't even worry about one-to-one function because it's not a function in the first place. So it's just not a function. We don't worry about one-to-one because if it'd be like saying, is that a car? If it's a car, tell me what color it is. Well, if it's not a car, you're not going to answer the second question, right? So the first part is it a function? Then if it's a function, is it a one-to-one function? So that's why we don't worry about the one-to-one part on that third box. Let's solve and evaluate some functions. We're going to start out with a table. Again, what is the name of this particular, what letter are they using for the name of this particular function? G. And we can see that right here, that you've got G of the input, and we can also see it right here, G of 3. So what is our answer going to be? What is our output if they ask us for G of 3? Do we see that that means the input value is 3, so our answer is going to be 7? So we could say G of 3 equals 7. And again, the whole benefit of function notation is they're really emphasizing the relationship of this input goes with this output. So they actually write them both down. They say, here's the input, 3. Here's the output, 7. What is G of, oh, this is a backwards question, isn't it? Because what did they say? They're asking you, what's the input if the output is 6? Do we see that? They're asking for the input this time if the output is 6. How does that change what we have to do? Because now they're not telling us the input, they're telling us, does that make sense? They're telling us the output this time? Okay, so where are we going to look for that output, that 6? Because where have we always looked before? We've always looked in the top row where the inputs are, right? If we're looking for the output, we have to look for in the second row. Do we have a problem here? What's the problem? Yeah. We actually have two answers. N could be 2, or N could be 4. Because there's two numbers that have an output value of 6, right? But still, the whole deal is we have to look here and then find out what was the input that gave you those outputs. So what does that tell us? If I try and do this in reverse, is this a function in reverse direction? No, because if I'm trying to use a 6 and get only one answer, it doesn't work. I get two different possibilities, right? So we can't do in reverse. We're going to talk about what that's called in a little bit. But that is, if we are given the output, that's how we still use our table. We look at the outputs and go back to what were the inputs. All right, so use the table shown, and let's evaluate G of 4. So look at the table. What do you think? What is G of 4 going to equal? Are they giving us the input or the output? input, right? And they're telling us the input is 4, so our goal is find the output. So what would it be? 6. Fairly easy. It's when they switch it around on us that's when it can be a little tricky. Well, let's do, oh, I thought we had another one there. Hang on, let me go back just to make sure. No, I guess we didn't. Okay. So we've looked at tables, right? We've done a lot of work with tables. We also want to look at graphs. So when we look at graphs, we still want to talk about how do we know if a graph is a function? And it has the same rule. Remember the rule for a table? Every input could only go to one output. Now, what does that look like on a graph? So let's take a look. Every input, so our inputs, does it make sense our inputs would be the x values? Okay, typically, unless they tell us something different. So let's say, for instance, if I looked at this first graph, if I had an input value of 1, does it make sense that the output would be this number down here, -3? And if my input value is 0, my output value would be right there, 0. If my input value was -1, my output value would be pretty close to +3, right? If my input value was -3, I'd go down here and it would be something really negative, like -10 maybe, okay? Is there ever a time where I could ask you f of whatever number and you'd get more than one answer from this picture? No, because you go straight up or down to find where the function is, right? Or where the graph goes, is a function. Now I'm going to make a mental note here. I have to do this part in a second, but I'm going to come back to it after we talk about functions. Okay, how about this one? Do you think this one would be a function? For every input, would you get only one output? Yeah. If I asked you for -1, there it is. If I ask you for -3, there it is. If I ask you for 2, there it is. Okay, so yes, this one is also a function. Okay, what about this last one? It's a circle. It's a very nice shape. Do we think that this one is a function or not? No. Now, what's the problem? If I give you an input of 1, you notice I could have this point up here, or I could have this point down here. I get 2 outputs with an input of 1. So that is not a function. And that leads us to something we call the vertical line test. Do you remember hearing that before, the vertical line test? So in other words, if you can draw a vertical line and it touches the graph twice, that graph is not a function. So that's why you'll see we've got all these vertical lines that I was drawing to find the function value. If it ever touches that vertical line twice, it's not a function. So that's why these first two are okay, and this one is not okay. Now let's go back and let's figure out, are these going to be, let's use blue, are these going to be one-to-one functions? How can we figure that out? Okay, I'm going to erase my red lines here for function. There's something called a horizontal line test. Once you know it's a function already, you can use the horizontal line test. And the rule for a horizontal line test is very similar to the vertical line test. If any horizontal line intersects the graph more than once, it's not one-to-one. So is this first one going to be one-to-one? No, because it hits 3 times in this particular spot. So not one-to-one. Now the reason for that is that means these y values are the outputs, right? That means an input value close to -2 gives me that value, an input value close to 0 gives me that value, and also an input value close to 2 gives me that value. So I've got multiple values giving me the same output. That doesn't happen in one-to-one. If you think about the table, it'd be like -2 and 0 and +2, and they would all have outputs of like 1/2. You see how that means it's not one-to-one? Because you're having different inputs giving you the same output. How about the second one? This line. Is this line going to be a one-to-one function if we think about the horizontal line test? Yeah, because any horizontal line I draw can only touch it once, right? So that is one-to-one. I'm abbreviating. All right, now, what about the third graph? Remember, we don't even care. Why not? It's not a function in the first place. So we don't even worry about answering that question. Because the question is it a one-to-one function? If it's not a function, it can't be a one-to-one function. So let me just quickly draw a couple more here for you to take a quick look at. How about this shape right here? Function or not a function? Function. One-to-one? No, because you're going to have the horizontal line test will fail. How about this one? Function or not a function? Not a function, because the vertical line test fails. So what does that mean about the second question? We don't even care. It's not a function in the first place. So there's a lot of different shapes, but you can always tell if it's a function or not, and if it's one-to-one function or not, by using the vertical line test and the horizontal line test. So that makes things really nice for us, if we can see the graph. Okay, and this is what we were just talking about. If any vertical line intersects the graph of an equation more than once, so any vertical line intersects more than once, then that equation is not a function. Okay, horizontal line test. Once you've determined that it is a function, because otherwise we don't care, then if any horizontal line intersects the graph of the function more than once again, the function is not one-to-one. So let's just ask, is this a function? Is it one-to-one? No, it is a function. It is not one-to-one. Since it is a function, f of 2, let's figure out the answer to that. Now, remember, they're giving us an input value of 2, correct? Which means we're using an x value of 2. So we go over here to when x is 2, right here, and we go up and we find the value of the function. And what is it? 1. F of 2 equals 1. Just from looking at the graph, right? No math to really do there. Just look at the graph. Now, how about this one? We already know it's not one-to-one, so we might get more than one answer to this, right? Because this time, what are they giving us? They're giving us the output, which is 4. So how do we do this one? Well, we've got to find out when is the y value, the output value, equal to 4. That happens right here. It also happens right there. So how do I find these input values that give us output values of 4? So we would say x is going to have 2 possibilities, right? How do we find those possibilities? What are the 2 x values that give us output values of 4? Yeah, -1. How do we find it? Well, we just go down and we figure out, well, what's the x value that goes with that? -1 is one of them. What's the other one? We just go down or straight up, one or the other, and we find out 3 is the other one. Either x is -1 or x is 4. Either one of, whoops, not 4, 3. Either one of those would give us an output value of 4. So we've done graphs and we've done function or graphs and tables now. Let's try one more here. I think this is the same graph. What do you think? You guys look at the graph. What do you think we would get? Are we looking for an input value or an output value? Input, right? They're giving us the output. So what do you guys think would be the answers for this one? Okay, I hear x equals 0 and x equals, what was the other one? 2. And you are correct because the function has a value of 1 at these 2 points. We go back and look at what the input values are, and the input values are 0 and 2. Now, usually the last way, besides the table and besides the graph, that we think about functions is with equations or formulas. So we're going to do this one, example 10. Express the relationship 2n plus 6p equals 12 as a function p equals f of n if possible. In other words, we want to get the p by itself and then the n's on the other side. So we're going to take this equation, this formula, and we're going to try and get the p by itself using algebra. So what would we do first? So we actually want to get the p by itself and want to cancel out everything else that's over there by the p. So remember, we start with the furthest away stuff from the p. How do we get rid of that 2n? Subtract it. So we're going to subtract 2n. I don't want to underline that, so we think it's division. we're going to subtract 2n. That cancels that to a 0. So all we have left on the left-hand side is 6p, and now we have 12 minus 2n, because those are not like terms. We cannot combine them. What else do we have to get rid of? The 6, because we want p to be all by itself. Divide everything by 6. And you're exactly right when you say divide everything by 6. This gives us just p. 12 divided by 6 is 2. And then we can view the numbers separately from the n. We can just leave the n next to it here. But what is 2 divided by 6? A 1 on the top and a 3 on the bottom? So that is our function. So, and the way they put in the book, they may want to see something like this. F of n equals 2 minus 1/3 n. So that it's actually written in function form. And then we know that from this, p equals the f of n. So once we figure that out, we just replace the p with the f of n, and that's function notation. Express this relation as a function of y equals f of x if possible. So we want to get the what by itself. They're telling us to get the y by itself, right? So what would we do first? Subtract x squared. So that cancels out. We've got y squared equals 1 minus x squared. Then we've got to get rid of that little 2, that exponent of a 2, right? How do we get rid of that? Yeah, we take the square root of both sides. And when we do this, we get a y. Does anybody remember what we have to remember to do anytime we take the square root of both sides of an equation? Anytime we do that, we have to put in a plus or minus, right? Because if I ask you, if you've got an equation like x squared equals 9, and you take the square root of both sides and you just get x equals 3, well, that's true, but that's not all the answers. It's not only 3 squared that equals 9, it's also negative 3 squared equals 9, right? So we have to put in a plus or minus. What that means is this plus or minus tells us this is not a function. So when it says if possible, this one is, you just have to say it's not a function. So it's not possible. Because you're going to get, for every input, you're going to get a positive and a negative answer as an output. So that's why that plus or minus makes it not a function. If nobody has any questions, let's continue on with example 13. And we are given this function, h of p equals p squared plus 2p, and we're supposed to evaluate h of 4. So if you remember yesterday, we were talking about the input value and the output value. What are they giving us when they tell us h of 4? Is that the input value or the output value? It's the input, because it's inside that parentheses. That's where the input always goes. The output is going to be equals whatever. So this is our input value. And that means for this function, we're going to have h of 4. And everywhere we see a p, we're going to replace it with our new input value, which is a 4. And then we just do the math. What is 4 squared? 16. And what is 2 times 4? 8. So we have h of 4, and that will equal 24. So our output value is 24 when the input value is a 4. Next one is same function, but this time, what are we given? We're not given the input value this time. We're supposed to figure that out. We are given the output value, right? Now, we haven't seen these as much as the other one. The other ones we kind of do a lot of, but what do we have to do in this problem to be able to figure out what the input is, what p is? Once you see it once, you'll be like, oh yeah, that's really easy. I can do that. What do we know that h of p equals? What did they tell us? It equals 3, right? So can't we just go over here and say, oh, here's an h of p. What can we put in for that? A 3. So we just replace the h of p with a 3, and then we're going to be able to figure out what p equals. Now, it has been a while since you've seen these, but this is a quadratic equation, right? Because it has a squared in it. So here's our squared, and our strategy for quadratics is we're going to move everything over to one side so that we have 0 on the other side. So we're going to subtract 3. 0 equals p squared plus 2p minus 3. Now, do you remember how we try to solve this? We've got a couple methods. Any ideas? What's that? Factor it. Factoring would be good, and in this case, factoring works, so we like that. And when we factor, a lot of times if there's no number in front of that p squared, we know it's just going to be parentheses, and what's going to have to go first in each of these parentheses so that it multiplies together to be a p squared. It's going to be p here and p here, because when we multiply those together, we get p squared. Then, at least the way I always teach it, then what I want to know is I want to figure out what's going on with these numbers over here, right? And the first thing I look at is this, because I know that these two numbers multiply together to be a -3. So what does that mean about the signs of those numbers if they multiply together to be a -3? They're different signs, right? That's how you get a negative when you multiply. One's positive, one's negative. So I'm going to go ahead and put that in here, positive, negative. Then we can look at this sign, and what does that sign tell us? Because in the middle sign, the middle number, we get that from adding those two numbers together. So if you add two numbers together and they have different signs, what does it mean if the answer ends up being positive? The bigger one is positive. So I like to just write a really big plus sign and a small negative sign. And then if we look at this -3, what are the options for factors of -3? Well, a 1 and a 3, right? And we know from what we just were talking about, the bigger one should be positive and the smaller one should be a negative. Is that going to work out? Does that multiply to be -3 and also add up to be a 2? Yeah, so then we know this can be plus 3 and minus 1. So we've got it factored, but we're not done. What do we do now to figure out the answers for P? Because it was important that there's a 0 over here. Because remember what this is saying? This times this equals 0. What's the only way to get a 0 when you multiply? Multiply by 0, right? So here's how we figure out this answer. If P plus 3 equals 0, that will make this a true statement. And also if P minus 1 equals 0, that will make this a true statement. And then we just solve each of these little equations. Well, if P plus 3 equals 0, P is equal to -3. And then over here, if P minus 1 equals 0, then P has to be equal to, just do our algebra, add 1 to both sides. Subtract 3 from both sides here. Those are just short ones, so a lot of times we don't write it down. But our two answers are P could be -3 or P could be 1. And remember what that means is, if our input value is a -3 and we plug it in, we'll get a 3. If our input value is a 1 and we plug it in, we'll get a 3. That's what that's telling us. If they give us the output, we're going to replace the h of P and figure out the answer from there. If they give us the input, we just plug it in and evaluate. Now we're to that back page, and we're going to be coming back to this back page several times on our notes, because these are going to be kind of like in previous classes, we've called them the parent functions. This particular book calls them the toolkit functions, but we're going to refer back to these a lot of times because these are kind of the main types of functions that we will be dealing with. The first one here is linear. If you look at the graph, it is a straight line, right? So it's a linear function. And in this case, it is a constant. A constant function is always horizontal like this. That's because the value of the function never changes. In this particular case, it's always a 2, right? The output is always a 2, no matter what x value you're looking at. So the general equation for a constant function is f of x equals c, some number. And c is just a constant, some number. So anytime you see that, and again, we're just introducing these and we're going to come back to them multiple times, but that's our constant function. The next one is also linear, and it is called the identity function. And the identity function says whatever your input is, the output's going to be exactly the same. So if you look at all these ordered pairs, notice input is 1, output is 1. Input is 4, output is 4. Input is -2, output is -2. So that is the identity function, and that's the equation for that, f of x equals x. Okay, here's one that's made up of a couple lines that are joined together. This is the absolute value function. Remember that it's always going to have a V shape. And this is, again, this is the most basic absolute value function. So when you're talking about positive numbers, notice it acts just like the identity function, 1, 1, 3, 3, 5, 5. But on the opposite side, since it's absolute value, when you have an input of -2, the output is +2, right? Because the absolute value of -2 is 2. And then the same. So that's why it goes up in both directions, to the left and to the right. But that is our absolute value function. Is our first curve. So this one is the general family is that it's in the power family. It's a power function. And this one is a quadratic. And we just solved a quadratic. It's something that has an x squared in it. So the most basic one is just f of x equals x squared. And so you could make a t-chart for this if you wanted to, but this is the picture of what that looks like. Okay, and we'll be referring back to these. So anytime you have a homework problem and you need to look back, this is that back page there is what you've got all those right there. Another power function is the cubic, x cubed. And so you can see how the shape is kind of similar, but it's like the one side got flipped down, right? So that's the x cubed function. Another one that is a power function is the reciprocal function. Now, it doesn't maybe look like a power function, but the reason is because it can also be written as this with a -1. So that's what makes it in the power function family, because the exponent's a -1, the power. But it's the reciprocal function, and it looks like this. And again, we'll come back to this, but the reason this looks like this is when you take reciprocals, remember you flip the numerator and denominator around. So like when we put in a 2, our output is 1/2. When we put in a 3, our output is 1/3. Put in a 4, your output's 1/4. Then if you go over here and you put in a 1/2, your output's going to be a 2, and so on. And the same thing happens with the negatives. So you get these lines that are getting really, really close to 0 as the x values get big, and then really big output values when the x values get really close to 0 because of that reciprocal idea. The reciprocal squared, and again, this is a power function because, and we'll learn this later on, but it can be written as a power. But this one, again, looks similar to the reciprocal, except for it's up on both sides instead of being up on one side and down on the other side. And then we have the square root function. And the square root function is kind of different than the rest. It starts at 0, 0. It doesn't have anything over here on the left, and it only goes to the right. And it actually turns out that it's like a sideways half of a parabola because it's related to the quadratic function that we talked about earlier. And that's parabola's quadratic function. And then we've got the cube root function, which is very similar to the x cubed function, except again, it's kind of a rotation idea. It's actually a reflection if you want to be really technical about it. So I should probably be somewhat technical about it. And so those are our toolkit functions. We're going to come back and we're going to talk about those pretty much every day for the next several. Okay, so you may not be an expert on any of them right now or on all of them right now, but we're going to come back and keep talking about them and keep talking about them so that hopefully they'll get in our minds and we'll remember those. Just as a reminder, as far as your homework goes, you can do the practice stuff as the section 1-1 practice as many times as you want, and it doesn't count against you. It doesn't count for you. It's just strictly that practice. There are 10 graded problems on the section 1-1 homework. That's what I will give you a grade on. But even on those, I gave you 2 chances to get it right.